In this series of videos, we will be looking at topics in Algebra 1. In this lesson, we will be discussing the different number systems.
All right, hi everybody. We're going to take a bit of a step back for a second and kind of look at numbers as a whole. Okay, I want to introduce to you guys this idea of number sets, groups of numbers that have similar related properties that are the distinctions are important to us. Okay, now to start off with, when we talk about number sets, really what we're doing here, if you follow along how I work through this, you are actually going to see a very kind of gentle evolution of these ideas, and you're going to see how this really relates back to your exposure to them as you're growing up. Because to start off with, we've got this set right here. Okay, this little circle here is going to represent the set of all of the natural numbers. Okay, these are the naturals. Now we use a little stylized n to refer to the natural numbers. Now, what's going on here is when I use a letter to represent a set of numbers, you're going to often see this additional little line in there. That is simply so that when I look at that n, and it's kind of a big fat n there, that in a math context, when I look at that n and I see that line there, I know that that n doesn't refer to a point, it doesn't refer to a line segment, it can only refer to the set of natural numbers. And these right here, and I'll come down here and we'll describe these over here. Here, the natural numbers, and we're going to use this letter n to represent them. This is just that set of numbers that starts with 1, 2, whoops, you can't even see that, 3, 4, 5, and so on. Okay? Just the counting numbers. When you learned to count, you started on the natural numbers. We call them natural numbers because they are the numbers that we naturally use when we start counting. Now we come up here, and there's a set of numbers that's just ever so slightly bigger than that. And now we call them the wholes. Whoops, and I spelled that wrong immediately. Wholes. Okay? W-H-O-L-E. I'll come down here. We'll do it down here. The wholes. The whole numbers. And we use, again, a little stylized W to refer to that. So up here, we're going to use this little W with that extra line there. Now, the difference between the natural numbers and the wholes is really only the presence of the zero. Same set of numbers. All we're going to do here is we're going to include the number 0. Now that might not seem like that big of a deal. I mean, so what? I'm just including the 0. But actually that 0 is an incredibly important addition to this number set. In fact, the introduction of the 0 really made it possible for a lot of the technology that we kind of love today to be possible. Okay, and I know that might seem like I'm really trying to sell that, but I don't think that's an understatement. Okay, so natural numbers, really just the counting numbers. Whole numbers, we include the zeros. And by the way, just so that you know here, we call them wholes typically, but not everybody uses this or even really identifies that as its own separate thing. A lot of times you're going to see people call these the non-negative integers. Okay, whoops, non-negative integers. Now we haven't even really gotten to what an integer is yet. We will like right in a second here, but I mean really, what's easier to say, non-negative integers or whole numbers? So anyway, we use the whole numbers. Now, beyond the whole numbers is a big set here, and this is what we call the integers. Now, based on how I'm building this up here, you might think, well, natural numbers n, whole numbers w, integers would be I, but actually they're not. We use the symbol z, okay? And that's because the Germans did a lot of work with number theory, with integers, okay? And their word for integer starts with a z. So down here, we have got the integers, and we use the letter z to represent the integers. And this kind of works like this. We can go basically infinitely to the left with all these negative numbers, and then -3, -2, -1, 0, 1, 2, 3, and so forth. So this actually works out both directions from the 0, with the negative numbers on the one side, the positive numbers on the other. But if you notice here, we're still talking really about these whole numbers. We've just added the negative sign to it. That's it. Okay? And that is interesting. And historically, a lot of people didn't like this idea of negative numbers. What the heck does negative even mean, right? It's ridiculous. And so it was an idea that took a lot of time to get some traction before people accepted that as really just a necessary tool in the arsenal of mathematics here. Now, what comes next? Well, after this comes everybody's favorite, rationals. Okay? And rationals, and we use the symbol, obviously, a Q for rationals. Not exactly sure why we use the Q, but we use the Q for rationals. Okay, so down here, rationals. And what are rationals? Well, okay, rationals are the set of numbers where we've got P over Q, where P and Q, whoops, are both elements of the integers. Okay, basically what we're talking about here are fractions. Now, often these get described as these are either repeating, okay, or terminating decimals. Repeating or terminating decimals. And so, for example, if I've got, let's say, 3/4, okay, integer over integer, and that is equivalent to the decimal representation 0.75. On the other hand, if I've got 1/3, again, integer over integer divided by integer here, its decimal representation is 0.33, and you know that's just 3 repeating here, and so sometimes you'll see people write it as 3 with a little 0.3 with a little bar over top. Okay, but that's the idea of a rational. It's this repeating or terminating decimal, but really what that means is that number can be written as a fraction, okay, as an integer divided by an integer, as a ratio. Okay, now, we know that whole numbers contain the naturals. Integers contain the whole numbers, which means they also contain the naturals. Rationals, okay, because one of the integers that I can use here is the integer number 1, and then P is an integer, notice that the rationals include all of the integers, which then means the rationals can include all of the wholes, which therefore means it includes all of the naturals. So these are why these are all subsets. The naturals are at the center, and then out the whole, integer rationals. Now, over here, then we get this set of irrational numbers. And one of the things I absolutely love about mathematics and mathematicians, okay? What symbol are we going to use for irrationals? Well, there's no overlap. This is a separate set of numbers. And by the way I've drawn this here is actually really radically misrepresenting the relationship in terms of the size. The set of irrational numbers is just absolutely huge. It like dwarfs this set of rationals here. It's massive. Okay. It's just that because I have set over set over set, I kind of had to make this one bigger. But this one here really, really is significantly larger than that set of rationals. But they don't overlap, okay? The irrationals do not contain the rationals, okay? This is the set. I'll show you the symbol here in just a second. The irrationals, rationals. I'll show the symbol here in just a moment. Basically, these cannot be written, okay, as P over Q, where P and Q are element of the integers. It's all the numbers where that's not possible. And so these are non-repeating and non-terminating decimals. I think I've gone off the screen there. Yeah, non-repeating, non-terminating decimals. And so the classic example of this is pi, right? 3.14159, it goes on and on forever. It never repeats, never terminates. Another really classic example is the square root of 2. And basically, if you take the square root of any number that's not a perfect square, you're going to get an irrational. That's because of the way prime numbers behave. And later on in your education, if this is kind of the first time you're seeing this here, you'll see what I mean by that. Okay, the square root of prime numbers really is the issue here. Now, granted, the square root of 10 would also be irrational. Okay, but that has to do with its prime number makeup, the 2 and the 5 in there, and that the fact that 10 is not a perfect square. Other examples that you might not be as familiar with is E. Okay, if you go look on your calculator, you're going to see that that letter E there. It'd be interesting to play with that button and see what happens there. And there are others. I mean, we put gamma, tau, and there's lots of other numbers. There's an enormous number of these things. Now, to the symbol. What I love about this, irrationals are numbers, if you take a look at the definition here, that really negate what a rational is. A rational is repeating or terminating. An irrational doesn't repeat, doesn't terminate. So it really is not rational. That little bar over top is the negation of it. It's not rational. I just love that. That's hilarious. Like, what symbol are we going to use? I don't know. Well, it's not rational. Anyway, whatever. I love those guys. Okay, now let's take a quick look at the last set that we're interested in, and that is going to be the set of numbers that basically encompasses all of this. Okay, it's the set that includes both of those, and these are what we call the reals. Okay, the real numbers. And again, the symbol is that little stylized R there, and basically this is all of the above. Now, we call them the real numbers, and that is because this is not the end of it. Now, this is about as far as we're going to go, okay? Because for most of what we're going to do in your kind of mandatory education, this is as far as you need to go. Now, some of you are going to go on and you're going to study the set of complex numbers, which includes something that we call imaginary. Okay, and that is in contrast to these real numbers. Okay, so you're going to see those. If those of you that go on, you're actually going to see that there are sets of numbers that actually intersect these, okay, in kind of weird different ways. We've got algebraic and non-algebraic numbers. Like, this is not the end of it. But I want to talk really briefly about why we use the word real. Okay, specifically as opposed to imaginary. Real numbers here can be used as a measurement. So just to give you a very, very straightforward idea, any measurement that you can make, okay, the number that you would use has got to be a real number. You can measure things, okay, with natural numbers. For example, you can people are running a race, you know, first, second, third, fourth. Now that's a specific type of natural number that we call an ordinal, but you can measure that with them. Whole numbers, right? I mean, we can measure things with zero. Okay, if your bank account is zero, I mean, you know what I'm talking about. Integers, we can measure, for example, temperature with integers as soon as we go into the negative degrees, okay, or your bank account, right? Just like we were doing before, you can actually overdraw and have negative money. Fractions. Okay, you can take a pizza, cut it into nice fractions. Irrationals. It is possible, for example, for you to measure the height of somebody, and it is an irrational number. You can, if you're going to measure the distance around the circle, you're going to find that if you've got a nice number as your radius, the circumference is going to be an irrational. Okay, all of those together become the reals. You can use those as measurements. If you start talking about imaginary numbers, they don't quite work that way. Okay, so real numbers, measurements, and then with the subsets here, naturals are within the wholes, or within the integers, or within the rationals. Irrationals are different. Together, they're all reals. Now let's just go through and classify a bunch of numbers. All right, Well, usually classification can go pretty quick here. So let's take a look at this. We start with negative 15. Well, negative 15. Immediately I know that that has got to be an integer. Okay, because of the negative in front there. That's the smallest set it could belong to. Now, it could also be a rational, because I can make that negative 15 over 1. Or I can even make it negative 30 over 2. Okay, and that would make it look like a rational. But typically what we do here when we classify these things, what we want to do is we want to put them in simplest form first. And I'll explain why in just a bit here. At least you'll see an example why in just a bit here. 11. Okay, well, the smallest set that could belong to is the naturals. Okay, it would also belong to the wholes. It is an integer, and then as a result, it's also a rational. Okay, and that's just because it belongs primarily in the naturals, and all of those are sets of each other. The square root of 30. Now, if you were to plug that in your calculator, you're going to get a kind of a weird-looking decimal there. Thing is, with your calculator, you're not quite sure if that terminates or if it repeats. Okay, but think of it like this: is 30 a perfect square? So, like when I take the square root of 30, do I get just a nice number? And the answer is no. So that is not rational. It's irrational. 17 over 3. Now that is a fraction, an integer over an integer. Now, can I simplify that? Okay, can I simplify that? Is 17 divisible by 3? No. So the smallest group that this could belong to is the rationals. 6. Well, just like the one above it, 6 is a natural, which makes it automatically a whole, which makes it automatically an integer, which makes it a rational. 0. Well, 0 is by definition a whole number. Not a natural, it's got to be a whole number. But that makes it an integer, and that makes it automatically a rational. Negative 13. Okay, well, the presence of the negative there suggests to me that could be, it could be an irrational, it could be a rational, whatever. But because of the way this is written here, notice it's like a negative whole number or a negative natural number. So really the smallest unit set it could be part of is the integers. And then as a result, it could also be a rational. Because irrational numbers can be negative as well. There's just a lot more going on there. 3. Well, you're noticing a little bit of a pattern here. Okay, that is definitely a natural. It is also a whole. It is also an integer, and it is also, because it belongs to all those, it is also a rational. Okay, and now this next one. 10 over 11. Now that doesn't simplify, okay, because there's no common factors between 10 and 11. So the smallest set that this could possibly belong to is the set of rationals. And then that's it here, okay? Now, by the way, it should go without saying, I haven't really done this at this point here, but, well, actually, I'll hold off on that. I'll come back to that in just a bit here. There's one more thing I was going to add to that, but I'll do that in a bit here. 14. Okay, well, 14 is a natural. It is a whole, it is an integer, and it is a rational. Okay, because it belongs to the naturals, belongs to all those. Negative 13, actually negative 13 is repeated there. That's really odd. Okay, already dealt with this one. That was integer and rational. Apparently that's a really important number to me. Okay, pi. Well, okay, pi. Pi is your classic example of an irrational, so not rational. All right, now, 475 over 325. Now, I know that this can be reduced, okay? I know that this can be reduced, but I don't believe that I can take 475 and divide it by 325 and get a nice number. I think you're going to be left with a rational here. So, as a result, we're going to classify this as rational, even though that can be simplified. It can't be completely simplified so that it's a smaller number set. I mean, it'd be great if I could pull like an integer out of that, or a natural number, but I don't think I can. Square root of 77, all right, well, 77 is 7 multiplied by 11. And that's not a perfect square, so I can't take the square root of that. So the square root of 77 is going to have to be an irrational number. Okay, 6 over 7, well, that immediately looks to me like that's going to be a rational. And because I can't simplify 6/7 any further than that, there is no smaller group that I can say that it belongs to. So the best I can say is that is a rational. Okay, square root of 0. Okay, well, don't let the presence of the square root throw you off here. The square root of 0 is 0. And so that makes this one a whole. Okay, because of the 0 makes that an integer, and then necessarily a rational. And this is where we're starting to get into some of these other systems here. So for example, this one right here, because of the square root, it looks like that might be an irrational number here, but it turns out the square root of 196 is 14. And so the smallest group that this could belong to, now because of that negative, like I would say, well, 14, that would be a natural, but because of the negative, that makes it an integer is the smallest group it could belong to. And then actually rational. That is in fact rational because this is that exception to the rule. -1? Okay, well -1, I mean 1 is your basic natural number, but as soon as you throw a negative in there, it becomes an integer. And so that -1 is both integer and rational. Now, okay, over here, this can be simplified. -16 over -2 actually becomes +8. So because this is equivalent to a much simpler number, and I know that that number is a natural, this number here belongs, although it clearly belongs to the rationals, okay, it also belongs to the naturals, the wholes, the rationals, well, I skipped the integer, and the integers, because that's a nice integer. Same thing over here with -135 over -3. Well, 135, okay, is in fact divisible by 3. And in fact, that is going to be -45. And so, without the negative, that would be a natural as the smallest set it belongs to. But with that negative, that makes that an integer. And then the integers belong to the rationals. Now, I'm going to go back here. The one set that we didn't refer to is the reals. And that's because that's a real, 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 that's a real. Like they're all reals. I could do that for all of these all the way down, include them in the reals. We haven't looked at imaginary numbers. And so at this point here, and when you do, it will be abundantly clear when you're dealing with imaginary numbers here. But yeah, all of these are also real numbers, and so just be aware of that. So I'm going to stop videoing right now because probably the last thing you want to see is me go through and put R's in all of this.